Hello class, this is Dr. Viv, and this is one of the tops I picked up from my top collection. So the topic for today is going to be rotational kinetic energy. So trying to figure out how to make sense of the kinetic energy of something that is rigid and rotating like that. So let's start by modeling it as something really simple. So I'm going to think of it as some random pear-shaped object. So let me draw a representation of the top here. So it's some object that's rigid and it's rotating about an axis of rotation, which I'll indicate like that. And if you want to call it the z-axis, but it can be any axis. So what's a rigid body? First of all, a rigid body is a construct such that every part of the object moves at the same angular velocity. So if I take a mass point and I call that mass point m sub I and look at its trajectory or the path it takes as this spins around, that path is going to be a little circle, and let's call the radius of that circle r sub I. So as the mass point wanders around, it's going to make a circle of radius r sub I for every revolution. And if the angular velocity is omega, some angular velocity, so if you remember our angular velocity convention, even though I draw it as a curved arrow, it really is in the z direction, because if I curve my right hand fingers in the direction of rotation, the thumb gives you the direction of the angular velocity. So let's try to find the kinetic energy of just that mass point mi. At any given time, it's got a tangential velocity, v tangential sub I. So let's try to write an expression for the kinetic energy of this mass point. I'll call it KEI. Now kinetic energy is just 1/2 mv squared, so I'll just write it as 1/2 mi vti squared. Now, from our understanding of rotational motion, the connection between the translational velocity and the rotational velocity is the following. Vti equals Ri times omega I. Well, it's omega I, but since omega I is the same for all mass points, I'm just going to call it Ri omega. So that in fact is the definition of a rigid body. A rigid body, so let's make a note of it. A rigid body is defined simply as the following. Omega I equals omega for all mass points mi. That is what makes a rigid body rigid. So now that we have this, we can substitute it in our formula for the kinetic energy. The kinetic energy of the ith particle is 1/2 mi Ri squared omega squared. Now the kinetic energy of the entire rigid body is got by summing up these individual mass point kinetic energies. So I'll call the kinetic energy of the entire rigid body the rotational kinetic energy, Ke rot, and that is going to be the sum of over all the mass points, Kei. Now when I perform the summation, let me just write it out first. It's going to be 1/2 mi Ri squared omega squared. Now the 1/2 and the omega squared are really not participating in the summation because they do not have the index I anywhere, so I can actually take it out. So I'm going to get 1/2 omega squared times the sum over all I, mi Ri squared. Now this is the quantity that needs to be defined. This is called the rotational inertia, I, moment of inertia about the z-axis. So I'll write it out in full. So this gives us a very nice compact looking formula. The kinetic energy of rotation is equal to 1/2 I about the z-axis omega squared. Now if you compare it and contrast it with what we have for the translational kinetic energy, Ke trans, well, that's just 1/2 mv squared. So in a sense, this, you can think of this mass as linear inertia. Then in the same vein, this can be thought of, this Iz is called the moment of inertia. Linear inertia tells us how easy or how hard it is to move something and how much energy is locked up in the motion of that thing. Rotational inertia gives us the same kind of information. How hard is it to rotate this top? I can just flick it with my finger, but some tops are obviously heavier than others, and so it takes more than just a flick of the finger to get them moving. And once you get them moving, the bigger the top, the more energy it stores. And it's not just how massive it is, but also how that mass is distributed, because you can see that in the moment of inertia is information about the mass as well as the spread. So if you have two tops of the same mass, one of them can be very close to the axis of rotation and it would not spin very much at all. It would not carry much rotational energy, but the other one can be flat like this. Even though there's a very lightweight top, it is actually spins for a long time because it's able to keep its energy locked up in a high degree of moment of inertia, since much of the mass is spread out. So this is the concept of both rotational kinetic energy and the concept of moment of inertia that I introduced by just examining a pretty humble finger top. I was told by the antique dealer that this was an ancient Russian top. It was cheap, so I just bought it.